Hello and welcome back to the course on algorithms. In this video, we are going to discuss chain multiplication problem. We will design an efficient algorithm based on the dynamic programming to compute the most efficient way of multiplying given n matrices. So in this matrices, we are given n matrices of different size, and our objective is to multiply these matrices, and we want to multiply these matrices in such a way that the number of multiplications that are involved is minimum. So given two matrices A and B, if you want to multiply A and B, we know that the number of columns in the first one, the number of columns in the first one should be exactly equal to the number of rows in the second one. So we can multiply a P cross Q matrix with a Q cross R matrix. If you have to multiply P cross Q matrix with a Q cross R matrix, the number of multiplications that are required is P into Q into R, right? So let's quickly see an example where different ways of multiplying actually gives us different number of multiplications that are required. So if I am given matrices, let's say ABC, um, if I want to multiply them in the order A into B into C, so matrix multiplication actually follows what is known as associative property. So you can either first multiply A with B and then multiply to the right by C. Other way of multiplying could be that you just multiply B and C first, and then to the left of it you multiply by A. So since the matrix multiplication satisfies the associative property, when it doesn't matter the order in which you multiply these matrices, you will always get the same answer. The resultant matrix will be the same, right? So which is equal to this. But we will quickly see an example here where the number of multiplications involved in multiplying in these two different ways are different. Let's say that I have A which is 10 cross 100 matrix, and B is a 100 cross 5 matrix, and C is a 5 cross 50 matrix. If I choose the first method where I multiply A and B, if I had to multiply A and B, since A is of size 10 into 100 and B is of 100 into 5, so the total number of multiplications that are required is 10 into 100 into 5, right? So this is already 5000, right? So when I multiply A into B, I get a matrix of size 10 cross 5. So now if I have to multiply with C, which is 5 cross 10, so the total number of multiplications involved in multiplying C to the right will be 10 into 5 into 50. So this is 5000 plus this will be the first one is yeah, so this is 5000 plus the second one. When I multiply, I get it about 2500, right? So this is 10 into 5 into 50 is 2500. So 5000 plus 2500 is 7500. The other alternative way of multiplying is that you multiply B and C first. If you have to multiply B and C, so what you have to do is that so we will take time. The number of multiplications involved will be 100 into 5, that is the size of the B. Size of C is 5 into 50, so this will take the total computations in total number of multiplications required to multiply B cross C is 100 into 5 into 50, and the resultant matrix will be 100 into 50. So if I have to multiply this to the left by a matrix A which is 10 cross 100, then it's going to take 10 into 100 into 50 number of multiplications, right? So if you simplify this, if you compute this, this will be total number will be here, this will be 75,000, right? So if you choose the first method, if you multiply A into B and then multiply with C, then you only spend 75, you will have to do only 7,500 multiplications. But if you first multiply B and C and then multiply with A, then the number of multiplications is 75,000. So in this case, the first method, multiplying starting with multiplying A and B and then multiplying with C is more efficient compared to the second method. So given n matrices, let's say that A1, A2, An, you'll have to multiply n minus 1 matrices and to get the final answer. So as we have seen here, the order in which you multiply these matrices do matter. So the matrix chain multiplication problem is to figure out what is the order in which you have to multiply these matrices, so that the total number of total number of multiplications, number multiplications that we are doing is minimum. So before we get into the DP algorithm, let's try to understand, in worst case, if I had to look at all possible ways of multiplying matrices and pick the one which is best, will this be a polynomial type? So we want to quickly see that this brute force method, which will look at all possible ways of multiplying matrices and picking the one which is the minimum, will be exponential. So in order to get this equation, so let's consider this. Let's say P of n is the, so is the P of n denote the number of alternate parentheses possible given a sequence of n matrices. So what is given here is that A1, A2, An is given. So we given a sequence of size of these matrices, given P of P0, P1, P of n. So the assumption here is that A1 is of the A1 is of the size P of 0 cross P of 1, and A2 is P1 cross Pi. In general, our assumption here is that A of I is a matrix of size P of I minus 1 cross P of I. Right, so the first one is P of 0 into P of 1, the second one is P of 1 into P of 2. So we know that the size of P of 1 here should be same as this, only then the matrix multiplication is well defined. So given this A1, A2, An, so let's say that there are n numbers. So I can decide to, I can put a parenthesis here and decide to matrix multiply these numbers first, and then decide to multiply the rest of these numbers. Let's say that I break this at the location k. So if I define P of n to be the number of ways of multiplying n matrices, then so the total number of, so I can, this k can be from anywhere from 1 to n minus 1, right? So I can first k can be anywhere from 2 to n minus 1, right? So if I give you the first matrix, this will be one matrix, and from 2 to n, right? So what we can do is that if this is the case, if I put the first parenthesis at k, then the number of ways I can multiply the matrix on the left hand side is given by P of k, because there are k number of matrices, and on the right hand side there are n minus k matrices. So the number of ways of multiplying those matrices by recursion is P of n minus k. So the total number of ways of multiplying is that I can pick any one way of multiplying matrix on the left hand side, and then so I can pick any one way of multiplying on the left hand side and one way of picking on the right hand side, and so the total number of ways of multiplying will be P of k into P of n minus 1. So the total number of ways of multiplying these matrices P of n, so will be equal to summation of P of k into P of n minus k, right? So where k is going from 1 to n, right? So in summary, what we have seen is that if P of n is the number of ways of multiplying n matrices, then P of n will be exactly equal to P of k into P of n minus k, where k is going from 1 to n. So this is true as long as there are more than, we can actually write n is greater than 2. So, right, if there are two matrices, then so P of 2 is, there is a unique way of multiplying two matrices, and the P of n is not defined for n smaller than 2, right? So P of 2 is, there is only one way of multiplying, and if n is greater than 2, then we can get this equation. We will not make an attempt to solve this recursion, so, but what I will show you is that this by induction will be omega of 2 to the power n. Okay, so let's say that I want to show that P of n by induction, P of n is greater than or equal to 2 to the power n minus 2, right. So, the base case is n is 2. So, this is only true for all the values of n greater than 2. So, if I plug in the value of n is equal to 2, then what I get is that P of 2 is by this equation greater than or equal to 2 to the power 2 minus 0, which is 0, which is 1. So, the equation is true for the base case. For n is equal to 2, the total number of ways of multiplying the matrices by this equation is 1, which is true. So, now let us come back to the general P of n. So, this is summation is going from 1 to n. So, this P of n, I will only pick the first term here and the last term here. So, this is certainly greater than or equal to, I will pick the value for k is equal to 1. If k is equal to 1, it is P of 1. So, P of 1 by definition is 1. And what I get on the right hand side, other term that I have is P of n minus 1 plus for k is equal to n minus 1. So, the P of, so what I get is P of n minus 1, and what I have on the other term that I get is n minus 1, which is P of 1. So, P of 1 is again 1, right. So, I do not have to multiply. So, the P of n by this equation is certainly greater than or equal to 2 into P of n minus 1. By induction, P of n is greater than or equal to 2 into n minus 1 minus 1, which is n minus 3. So, which implies that 2 into n minus 2 into 2 to the power n minus 3, which is equal to 2 to the power n minus 2. So, by induction we have shown that P of n is greater than or equal to 2 to the power n, which essentially means that if you apply the brute force algorithm to figure out all the method, all the ways in which we can multiply this algorithm, then the number of steps that are involved is at least 2 to the power n minus 2. So, the brute force way of finding out what is the best way to multiply n matrices is has a lower bound of 2, is an exponential time algorithm. For example, if there are 100 matrices that are given to us, this particular algorithm cannot be used. So, now we have already seen, but from this brute force analysis, so whatever analysis that we have done here will give us an idea, right. So, there is a recursive overlapping subproblem that we have already considered. So, what was the main idea in designing this is the following. So, we break it at a particular value of k, right. So, given the matrices that I want to multiply from let us say from I to j. So, okay. So, we ask the question, what is the first matrix that I am going to multiply? Let us say that I am going to multiply the matrix, I am going to break it at k, and the last matrix multiplication that I am going to do is I first recursively find from I to k, and then I recursively find from k multiply from k plus 1 to j, and so whatever these two matrices that I get will be multiplied. This is the last multiplication our algorithm does. So, the k can be between anywhere between I plus 1 and j minus 1, right. So, if this is the case, we can recursively compute what is the best way to multiply matrices from I to k and from k plus 1 to j, right. So, how do we compute the value for this? Let us define the cost of computing this. If I know that k is the place where I have to cut it, then the total cost of our algorithm will be cost of multiplying from I to k, the matrices from I to k, plus the cost of multiplying the matrices from k to j and multiplying these two matrices. So, the size of the matrix from I to k will be exactly equal to P of I minus 1 into P of k, and the size of the matrix on the right hand side, but k plus 1 to j will be exactly equal to P of k into P of j. So, the last matrix multiplication that I have to do will be of size P of I minus 1 into k, and the other matrix will be P of k into P of j. So if I have to multiply these two matrices, I know that the number of computations that I have to do is P of I minus 1 into P of k into P of j. So now let's define what is the state of the dynamic programming. It's clear now. So we will write m of I comma j be the minimum number of multiplications required to multiply the matrices from I to j. M of 1 comma will be our answer because our objective is to multiply the matrices from 1 to j. So from whatever we said here, so now that we define the state of the dynamic programming, we have to decide how to fill this table, right? So what we have seen earlier is that if you want to multiply from I to j, what first we do multiply from I to k, right? So this is I and this is k and this is j. Then you multiply the matrix from k to j, and then the last multiplication is these two matrices. So if I have to multiply from matrices from I to k, then the minimum number of matrix multiplications that are required is m of I comma j, I comma k by definition. So if I have to multiply matrices from k plus 1 to j, then the minimum number of multiplications required is given by this equation. Now the last multiplication that I have to do will cost us p of I minus 1 into p of k into p of j. See, among all possible values of k, we will pick the one which is minimum. The range for k is between I and j. It can be equal to I, but it has to be strictly smaller than j. Let's look at this algorithm with an example. So we have given 5 matrices, and notice that this table that I have defined here is only implicable for I is smaller than j, right? So it's easy to see that if a of I comma I is all going to be 0, so you don't have any matrix to multiply, and so the algorithm would naturally pick if I is I plus 1, then it is basically multiplying two adjacent matrices. If you look at 1 comma 2 here, this is the multiplication of a1 and a2. a1 is of size 1 cross 10 and a2 is of size 10 cross 5. So if you have to multiply these two matrices, the number of multiplications required is 1 into 10 into 5, which is 50. Similarly, if you have to multiply the matrix 4 and 5, the number of multiplications required will be 2 into 25 into 4, which will be 200. So now if you can apply the dynamic programming technique using the algorithm that we just described, we get this table. Let's just look at how to get the 60. So this is the product of A1 over A3. Let's first look at how to get if I have to multiply A2 and A3, and then if I have to multiply to the left by A1, then if I have to multiply A2 and A3, the number of computations involved will be 10 into 5 into 2, which is 100. And if I have to multiply to the left by A1, then the number of computations involved will be 1 into 10 into 2, which is again 20. So this will be total number of computations will be 100 plus 20, which is 120. But the other way around, if I have to multiply a1 and a2 first and then multiply to the right by a3, if I have to multiply a1 and a2, I already know that the number of computations required is 50, and if I have to multiply to the right by a3, then the number of computations required is 1 into 5 into 2, which is 10. So the total number of computations required will be 50 plus 1, which is 60, right? So 50 plus 10, which is 60. The other option was looking at a2 and a3 first. If I have to multiply a2 and a3, this already takes 100 computations, right? So this is not optimum, right? So the 60 is the optimum. Let's look at how to get this. The there are 4 different ways of multiplying. The k will take values between 1 and k. Let's say look at the value of k to be 4. In that case, first we recursively compute the product of the matrices from 1 to 4. If I have to compute the matrices from 1 to 4 from this table, the best way to compute the product of first four matrices would require us 110 multiplications. Then if I have to multiply the A5 to the right, then the total number of multiplications required for that will be 1 into 25 into 4, which is 100. So total number of computations that we have to do, if you choose this option, is 110 plus 100, which is 210. So that's what happens to be the minimum. If you explore every other option, we will see that the number that we are going to get will be more than 210. So if k is 3, that means that you want to multiply the first three matrices, then you multiply for matrix 4 and 5, and then multiply these two matrices. If I have to multiply the matrices A1 to A1, A2, A3, then the number of computations that it requires is 60. And if you want to multiply A4 and A5, this requires 200. So 200 plus 60 is already greater than 210. So multiplying the first three matrices is not a good option. The other option is multiplying A1 and A2, then multiply A3 to A5. So if I have to multiply A3 to A5, this will take 200 number of computations. If I multiply A1 and A2, it will take 50 number of computations. 250 is already greater than 210, right? So we have to look at the ways to multiply A1 and A2. Then we have to look at how much computation it takes to multiply A3 to A5. Then we have to multiply these two matrices. So this 50 plus 200 plus the number of multiplications required to multiply these two product of matrices. So but 50 plus 200 itself is greater than 210, so this is not a good option. The last option is multiply A2 to A5 and then multiply A1 to the left. If I have to multiply A2 to A5, so if I have to start with A2 and multiply everything up to A5, then this table tells us that it requires 380 number of computations, which is already greater than 210. So among all the four different options that you have, the first one, that is recursively multiply A1 to A4 and then multiply A5 to the right, is the one which gives us 210 number of multiplications, and this is the minimum number of multiplications required to multiply these five matrices. So notice that unlike the three examples of dynamic programming that we have seen so far, in all the examples we were filling the table column wise or row wise. In this is an example where we fill the table column wise. Initially we set all the diagonal entries to be 0. After that we will fill the entry which is above the diagonal, these entries. Then we will fill these entries, and then we will fill these entries, and finally we will fill this. So this entry, when we want all the entries that are required to compute this, will already have been computed, right? So we will not be using the bottom half of the matrix as of now, but we will come back to see how this space can be used. Now let's look at quickly the code for this. So initially we will set t of I comma j. So instead of m, I am using the table as t of I comma j. So t of I comma j will be set as 0 for I is equal to t of I comma I will be set as 0. After that we will be looking at which of the diagonal we will be updating, right? So that is the length of we will call it as the length. This is the difference between j minus I. Then for I is equal to 1 to n, we will check we'll set our j to be I plus 1, and the k should ideally go from I to j, and we have to keep track of the minimum. So what I do is that I set k of I, and then I set for this particular value of k, whatever is the equation that I am getting, I will set it as t of I comma j. The t of I comma j, if I break it at k, first I have to multiply from I to k, then you multiply from k to j, and then multiply the two resulting matrices that we know that will require so many computations. So for k set as I, and then we go inside the loop. Here k will go from I plus 1 to j. So if this is the choice of k, this is where we are breaking, then this will be the number of multiplications to multiply a to k, k to j, and this is the this is the way to multiply these two final matrices. If T of I comma j is greater than this, then breaking at this particular k is better than what we had earlier. So the resulting number that we do after computing this is smaller than the present T of I comma j, then I update my T of I comma j to be is equal to T of I comma k, P of k plus 1 to j, and P of I minus 1 into P of k into P of j. So we also we only use the upper diagonal matrix to keep track of these entries, but whichever, when I compute T of I comma j, whichever k is giving me the value of T of I comma j, we want to store that in the T of j comma I, which is the lower triangular matrix, right? This will help us to do the backtracking, right? So since there are 3 loops here, and since we have to compute order n square, number of entries in the table, but computing each entry is order n, so the total complexity of this algorithm is order n cube, and it requires a table of size order n square. Now let's quickly look at what are these values which is written in the lower triangular matrix. So what they saying is that if I compute this T of 1 comma 5, so there is a k which will determine this value. That k value is given by 5 comma 1, which is 4. So that means that when you multiply a1 to a5, so what you need to do is that first you have to multiply a1 to a4, and then multiply to the right by a5. So since k is 4, will come here. This is the way to multiply from 1 to 4. So if I have to multiply from 1 to 4, the table T of 4 comma 1 will tell us what is the place where we have to break. This table tells us that 4 comma 1 is broken at 3. That means that if I have to multiply matrices from 1 to 4, first we have to multiply 1 to 3 and then multiply to the right by 4. So using we can use the lower triangular matrix in order to keep track of the k, which will give us the T of I comma j. I repeat, the T of I comma j is given by one of the values of k, where k is anywhere between I and j, and whichever k gives us the smallest, when I take the minimum, whichever gives us the minimum value of T of I comma k, that per I comma j, that particular k is kept track in T of j comma I. So whichever k gives us the minimum value of T of I comma j, that is being stored in T of j comma I. This will help us to do the backtracking. If you want to know how to multiply the matrices from I to j, and n is the size of the matrix that is given to us, and t is the table, right? So we compute the k. So k is T of j comma I. First you multiply the matrices from k to I to k, then you multiply from k to j, and then you multiply the two resulting matrices. That is, you have to basically multiply whatever you had on the left hand side, that is the sum of the product of the matrices from I to k has already been computed, and then you have to multiply the matrix from k plus 1 to j, right? So that's precisely what this algorithm says. So we will know exactly where is the k, so that you multiply from I to k recursively, and then multiply from k to j, and you get two matrices, and the last multiplication that you have to multiply is from beginning till end. In summary, the matrix chain multiplication problem can be solved in order n cube time and order n square space. In the table that we are building, in the upper half of the table, we will store the minimum number of multiplications required to multiply the matrices from I to j. So in order to compute T of I comma j, there is a value of k which will give us the minimum among all possible ways of multiplying. That is what is stored in the lower half of the table, that is in T of j comma I. Using this table which stores the value of k, we can figure out by backtracking exactly the way in which we can multiply these matrices in linear time. Okay. So as done in the previous three examples of the dynamic programming problems that we have seen here, I will still ask the question, if you are just interested in knowing the minimum number of multiplications, but Probably you don't want to do the backtracking and figure out how to multiply these matrices to get the minimum. In that case, can we have a linear space algorithm? The time will still be going to be cubic, but can we save on the space and do the everything in linear space compared to what we have done with quadratic space? The idea here is that in order to fill an entry, we have to see how many previous diagonal entries are required. I claim that if you maintain 3 diagonal entries, you should be able to fill the column. Hence, instead of maintaining a order n square table, if you just maintain a single array of length 3 into n, you should be able to compute the minimum number of computations which are required in order n cube time. Since we are maintaining a 3 into n table in this case, this will take linear space. I will leave it you to figure out the details how to do it. With that, we will end this video, take a break, and come back to the next set of videos in which we will see more problems which can be solved using dynamic programming technique.